Welcome to the short discussion on this topic, shear force and bending moment diagrams for cantilever beams. So in this particular short discussion, we are only considering the simple loadings. This is part of the unit 2, namely shear force and bending moment, the part of syllabus in strength of materials 1 course. I am hoping that by the end of this particular discussion, we'll be able to at least draw the shear force and bending moment diagram for the cantilever beams with UDL, which means uniformly distributed load and uniformly varying loads. Also able to construct the shear force and bending moment diagram for point loads and as well as when there are couples acting on the cantilever beams. Basically, there are two different ways, right? Which generally no will be two different concepts we will be using for the construction of the shear force and bending moment diagram. One is a quite systematic process called method of sections. The other one is it is simply based on the uh, shear force, bending moment, and loading relationships. Okay, so in this particular discussion, the second method we are using, okay, which is simple for a simple type of loadings, which is simple, right? So let us know first have some understanding on the relationship between the loading, shear force, as well as shear force and bending moment, right? So in one of my previous discussion, I have detailed that the relationship, how we get that relationship between the shear force and loading as well as bending moment and shear force. You can refer to that in case of any queries on that. But the conclusions I am going to discuss of that particular discussion before proceeding to the construction of the shear force and bending moment diagrams for the cantilever beams loaded with all basic type of loadings. Okay, so the relationship between the shear force and bending moment, particularly when in that particular situation we have considered a UDL, right? Although we consider the UDL, this concept can be extended to the point loads and uniformly varying loads also, right? After all, this concentrated load is a kind of UDL but acting at a short distance at a point, right? So the conclusions of that particular concept is you will be getting the rate of change of bending moment is nothing but the shear force. Another way of saying is the uh, difference between the bending moment ordinate between the two different points is equal to the area of the bending shear force diagram between those 2 points. Okay, this is one of the conclusion that resulting from the when we are trying to work out a relationship between the bending moment and shear force, right? The rate of change, or you can say the change between the bending moment at two different locations is nothing but the area of the shear force diagram between those 2 points. And similarly, if you want to get the variation in the shear force between two points, right, that dv by dx is nothing but rate of change of shear force is nothing but the load, which also can be written as the change between the shear force between those 2 points can be obtained by finding the area of the loading diagram between those 2 points. These are the conclusions actually. And apart from that, in relation to the loading as well as shear force and bending moment, you will be getting some kind of no idea about the shape of the curves, right? So UDL, when you are using, you will be getting the shear force as, because your load is in the loading is at a particular section is a linear function, then you will be getting the shear force as a linear function, whereas the bending moment is a quadratic second order function. All right, if you are having a point load, which means your zeroth order of the loading, then your shear force will be constant and your bending moment will be a linear curve, okay, or linear no variation. If you are having UVL, which means the kind of loading that you are taking, it might be what you call uh, it may be, suppose you are taken at a particular distance, there is a uniformly varying load acting, right? So when you try to calculate the the equivalent load of that, right? So that may be a second order magnitude of second order type, okay. In that case, the shear force shape will be quadratic and the bending moment will be cubic. So mostly you can see that if you are trying to convert that particular loads into point loads, whatever is the order, same thing is the order of the shear force, whereas the bending moment diagram is 1 degree excess, no extra than the shear force. Of course, when there is a couple, it will not have influence on the shear force, and the bending moment will be constant, or it take a sudden jump there, okay. Overall the relationship, the variation is going to be a constant. And then another conclusions, some other conclusions that we can what you call keep no notice during the topic of what you call that shear force bending moment relationship is the area, as I already discussed this, right? The area of the shear diagram, either to left or right of the section, is equal to bending moment at particular section. Of course, depending upon the shear diagram, whether it is, sometimes it may go upwards, that means gradually increasing, or sometimes it may gradually decreasing. Depending upon that, the main moment diagram is going to be either concave up or concave downwards, right? Or you can say concave downward can be also be represented as a convex shape, right? Now, with this particular fundamental understanding, we'll try to um, use this particular concept in the construction of the shear force and bending moment diagram in relation to the cantilever. Let's look at a simple loading here. So from now onwards, I am going to take all basic loads like UDL, point load, then UVL, and couple, all this basic loading on the cantilever beam, trying to construct the shear force and bending moment diagram. Just apply these very points which I discussed here. I am not going to use any, not even take section at any point, because that I will be discussing that in a separate session, that is going to take a method of sections. That is not use that concept of method of sections I am not using here. Simply I am using the relationship between the these shear force and bending moment as well as loading and shear force, okay. So these 3 points one should keep in mind for construction of the bending moment diagrams when you are using the concept of relations or relations among the loading, shear force and bending moment, right? So these 3 points keep, and you can apply these 3 points for all kinds of loading. It is applicable, and you can be able to construct your shear force and bending moment without any difficulty. Let's look at first one. Whenever you are drawing the in cantilever particularly, the advantage is that you can straight away start your shear force bending moment diagram construction from the free end. You don't have to even find the reactions also, right? Straight away you can start drawing your no shear force and bending moment diagram. The first step in the process is, when you are drawing the shear force bending moment diagram for a cantilever beam, is you should follow the sign convention, right? So when there is a section XX, you are on the left of the section. This kind of no what you call uh, forces acting, this kind of shear force is acting upwards, then I will be taking that as positive. And when the on the right of the section, if it is downward, then also I will be taking that particular one as positive. Similarly, moments left of the section clockwise positive, right of the section anti-clockwise is positive. The vice versa, in the sense, if it is in the reverse case, whereas no, in the reverse case, in the sense, in the left side of the section, on the left side of the section, if you are having downward force. Okay, then I will be saying that this particular shear force I will be taking negative, and right side if it is upwards, right, shear force acting on the right of the section is upwards, then I will be also taking that shear force as negative. Coming to the moment, the reverse of this, that means left of the section anti-clockwise and right of the section also anti-clockwise, that can be taken as this is anti-clockwise left of the section and right of the section also anti-clockwise, that is taken as a negative set. Okay, this is a preliminary sign convention to be followed, whether it is method of sections or whether using the what you call the relationship among loading, shear force and bending moment relations. Okay, so either way you should follow the sign conventions. So right now we can start. So first for that rough sketch you can make it straight away, it is not much difficult because the loading, as I told you in the previous slide, that when the loading is the loading is actually the first order, right? If you convert this into a point load, right, if you convert this into a point load, what is that? The total UDL is Wx, right? W equal to WL. Okay, so it is a kind of if it is acting at the x distance, of course we will say Wx. If it is acting over the entire distance, say WL. So what you are going to get is for a when the loading is UDL, right? What we discussed, when the loading is UDL, then your shear force will be a linear relationship. Okay, so at least you consider 2 or 3 points, right? Then it is easy to draw the shear force bending moment, shear force or bending moment diagram, right, without much difficulty. So at this location, okay, at this location the load has not yet started, right? So as by the definition of the shear force itself, because there are no forces acting here, so I am starting from the free end. What is the value of the shear force here? 0. Okay, now at this location, where here at this location, either any 2 or 3 points as I told you. So one you have taken already in the beginning, right? So up to distance lay, what is that? You take the, as you told, just now we discussed, if you want to get the shear force, you can simply find the area of the UDL wherever you require. Let us say I require the ordinate here. You find the area up to that particular point. Or if I want to shear force up to this, at this point, ordinate I want to find here. Find the area of the loading diagram up to this point. So up to this part, 3 points. Let us we will start with. We will take a 3 points. So let us find the area of the shear force up to here. So what is the ordinate here? If you want to get the ordinate here, you find the area. Let's say this is our point number 1, this is our point number 2, this is our point number 3. So if you want the shear force at the location 2, right, you find the area of the this loading diagram up to the point 2, right, from here to here. So what is this load? Area means simply multiplying the load with the distance over it is acting. Let the distance is, so center we are marking, so distance is L by 2. So what is the ordinate? W times L by 2. So W times L by 2. And this load, how loading is in the downward direction. So when we are moving from left to right, your section is on the right side, right, you are on the left side of the section, right? So when you are on the left side of the section, right, downward forces, this loading is a downward force, but we told downward forces are negative. So therefore you start you put the what you call the ordinate on the negative side, that is minus WL by 2. Okay, keep marking that WL by 2 is the ordinate here at second point, at the location of second point, right? So at the second point you can put the ordinate as WL by 2. So we marked that. This is the ordinate. Now if you want at the point 3, if you want at the point 3, you can find out the area, right, from 1 to 3. right? Not 2 to 3, 1 to 3. So you find 1 to 3, what is the area? W times L. So this ordinate will be WL. Let's say here, this ordinate is WL. Bus, you got it. So this is one point, this is another point, this is another point. How to join? I told you just now that when there is a UDL, your shear force is going to be linear. So you just put join all by means of a line. That's it. Minus. Okay. So this is the shape of the shear force diagram. That's all. Okay. Next, if you want bending moment diagram, again same thing. You should find the area of the shear force now. Right? Again you take the same 3 points. Say 1, 2 and 3. These are the 3 points. So at the location 0, before that to find any area, here nothing is there. So you can put again bending moment also 0 here. Whereas here, if you want to ordinate here, I should find the uh, I should find the area between these 2 points. So what is this area? This is a form of a triangle shape. What is the ordinate? WL by 2. This ordinate is WL. So base and height, half base height. This is L by 2, right? This is L by 2. This is also L by 2. So what is the area of this shear diagram? Half into WL by 2 times L by 2. How much is that? WL square by 4. WL square by 4. Sorry. WL square by 4. Similarly, if I want to ordinate here, you can put this entire area between here to here. So what is that? Here base is L and this particular height is this whole triangle I want. So WL times total, WL is the ordinate here, right? This is WL and what was the distance now? This whole distance, right? L by 2, right? So half times, what is the ordinate here? Earlier we got, right? WL, right? Half into no, WL, simply WL we got. So the, what is the area now between this point and this point? Okay, so that is half times WL times half times what you are getting, half times WL times L, right? So then what you are getting the ordinate as WL square. This ordinate is WL square. Ordinate at this location is WL square by 2. Half times WL times L. So you got this first ordinate 0, second ordinate WL square by 4, third ordinate WL square by 4. So join them, all of them. But how to join? By a line or by quadratic equation? We have discussed that. When there is a UDL, okay, when there is a UDL, the variation of the bending moment is quadratic. So join by a quadratic equation. So join them by a curve, right? Join by particular curve. Yes. That's it. This is your bending moment diagram. So thus we completed the shear force and bending moment construction for a cantilever. Now let us look at, so this is the diagram, right? WL here, WL square by 2 here, and 0 at the free end. Now you look at another type of loading. Let's say we will take a uniformly varying load. So if there is a uniformly varying load, then also you can apply the same points. You must consider the sign convention. You consider the type of load, what type of loading is there. Accordingly, you can keep varying your shear force and bending moment diagram shape, right? So here it is a uniformly varying load, right? As I told you, you don't have to even find the support reaction for drawing the shear force bending moment diagram in case of cantilevers with simple loading, right? So now you can start. So your shear force, again we will select 3 points, say 1 here, 2 here, and 3 here. Okay, you just mark the ordinates here using these very points. So if you want a shear force, take the area of the loading diagram. If you want the bending moment ordinates at these locations, you find the areas of the shear force diagram, obtain shear force diagram in the first step, right, in between the respective points, right? So let's see first one. If I want the ordinate here, what is the area of the shear force diagram up to this? Before this nothing is there, therefore the ordinate here becomes 0. So this ordinate is 0. Second ordinate, if I want ordinate here, you find the area of the loading diagram up to this, from here to here. So this, what for that I need, what is the ordinate here, right? So that is very simple to find the ordinate here. This triangle and this big triangle, these two are similar triangles. Therefore, based on that, I can find out this loading as Wx by L, because at a distance of L, okay, here I am taking a, let's say this distance I am assuming is as x, okay. At a distance of L, right, the loading is W naught. At a distance of x, it becomes proportionately W naught times W naught x by L, right? So I got the intensity also. Now what is the area of this diagram up to this point, because I am interested at this point. Say this is my point number 1, point number 2, point number 3. So at point number 1 I got the ordinate 0, point number 2 I have to get the ordinate. For that I am using the area of the loading diagram. So what is the area? This area is a triangular shape. So half into base is x and wx by L, right? So what is my area up to this point? If I consider this distance x, this is wx square by, right, wx square by 2L, right? Wx square by 2L. So wx square by 2L, if my point 2 is at the mid span, say, right, wx square by 2L you can take. So mid span means x becomes my L by 2. So in that case, what is the ordinate? X, that means L square by 4 again divided by 2L. That means what? WL square by 8, right? So what I will be getting finally? WL square here by 4 into 2. This L, one L get cancelled and you will be getting here an ordinate of WL by 8. This ordinate is WL by 8. This ordinate is WL by 8. Now you go to the point 3, right? Here, if you want the ordinate here, you find the area between 0 to 3, this whole area. So this is straightforward, half times W times x, okay, half times W times W naught times x. So what is the ordinate? Put x equal to, or L, right? You are taking at a distance L. So this becomes W x naught, W naught, this ordinate becomes W naught. This is also W naught, by the way. I have taken W, but the original loading is W naught. This is W naught, sorry, W naught W naught L by 8, right? That's what we got here. And here ordinate is going to be W naught L by 2 only. W naught L into L by 2. Okay. Now you join these three ordinates, you are going to get the SFD diagram. Right? How to join? I told you already. When there is a UVL, second order curve, join means of a curve. Quadratic curve, right? Second order curve. Quadratic variation you are going to get. So join by a curve. Alright. So this is your what you call shear force diagram, right? This is your SFD. Now if you are targeting for say bending moment, when you are going for bending moment, so you again also you take 3 points, say 0, sorry 1, 2 and 3, 3 points. So let us say at first point, what is the bending moment? For bending moment, what I told you, you take the area of the shear force diagram up to this location, right? So before that nothing is there, so this ordinate is going to be 0, and the left of this point nothing is there. We are moving from left to right, remember. When you want ordinate here, on left side of that 2 up to that point, you will find the area. So this going to be, this is not a linear by the way, right? This is a quadratic equation we just now told. Is a second order quadra, is don't forget no, don't mistakenly take it as a linear relation. It's a quadratic variation, right? Quadratic function. So because it is a quadratic function, what is the area of this particular, this, you know, it is a kind of parabolic curve, right? So the area of this particular one will be one third. If we assume this part is a rectangle, this is going to be one third of that rectangular area. So what is the ordinate here you are going to get, right? Here also this sign convention I forgot. The sign convention is, right, when you are moving from left to right, again it is a negative sign, right? And then this particular area, right, one third of this rectangular area. So one third of this distance is say L by 2, right? What's what we discussed earlier at the mid span, right? One third of what is the ordinate? L by 2 times W naught L by 8, right? That means this ordinate is going to be W naught L square by, already 2 is here, 8 is here, 16, and 1 by 3 is available in front, so it's going to be 48. So the ordinate is going to be 48. By the way, the bending moment also negative, because left of the section, we are moving from left to left of the section clockwise only positive, our moment is going to be anti-clockwise because the loading is coming this way. Okay, so this is W naught. What you are going to get is W naught, this ordinate you are going to get, and then again you take try to calculate, this is already over, W naught L square by 48. Keep this here. Now go to the last third coordinate, third ordinate at the point 3, right? So then you take the area of this entire shear force diagram. Again same, if you assume this whole location, the whole shape in this part as one full rectangle, one third of that rectangle only this area will occupy. So one third of L times, right, L times what is the ordinate here, W naught L by 2. So it's going to be W L square by 6. W, this ordinate is going to be W naught, this ordinate is going to be W naught L square by 6. So join all the three, you got the ordinates all three, join it, but by cubic curve. So more sharp than the previous curve. So this is your bending moment diagram. Okay. So this is how you will be getting. So if you want to see to the scale point of view, this is how you will get the curve perfectly, right? W naught L by 2, that's what we got, right? W naught L by 2 is ordinate and W naught L square by 6. Okay. Finally, if you have a point load, if you have a point load, how do you get the shear force diagram and bending moment diagram? Okay. So same, you follow the sign convention. This is much simpler even, right? And if you want shear force diagram, take the area of the loading diagram. If you want bending moment diagram, you take the area of the shear force diagram. Okay. So here, because it is a constant load, right? Here area in the sense, you don't have to even to multiply with the distance. You can directly proceed by taking the load magnitude, because the variation is going to be, when there is a point load, the variation of the shear force is going to be uh, constant, right? So whatever is the loads, keep adding the loads. That's what you have to do. You don't have to multiply the loads with the distances also. It is not a UDL, right? So you can simply add the keep loading. There is only one load, right? So that load, according to the sign convention, when you are on the left of the section, downward forces are negative. So you start from here, say W, okay, with the negative sign. On the negative side you can draw, and there are no other loads, so straight away extend this, okay, to the end. That is going to be our shear force diagram. This is your SFD. So it's very easy, right? Similarly, when you are drawing the bending moment diagram for this concentrated load, I told you, for this you can use simply area of the shear force diagram. So at the location, at the point 1, say here, okay, 0, because this there is no area, so this is 0. And if you want the ordinate at somewhere here, okay, you can even find out at the middle also, say point 2. Like earlier, we can also take 3 points here. First point 0, that is one first point, second point and third point. Bending moment also, because this kind of bending moment, the load into distance, right? So when you are on the left of the section, this kind of moment we have told negative. Okay, so this is a negative moment, so downward side only you can draw. So point 0 at a point 1, 0, and then here you take the area up to this part, then you will be getting the ordinate here. You take the area from beginning to here, then you get the area ordinate of this particular point 3. So up to this area, what is the area? It is WL by 2. So this ordinate is WL by 2. And up to this area, what is the area? Up to this point, what is the area? WL. Simply rectangular area, WL. Join all, because when there is a point load, the variation of the bending moment is linear, joined by a linear line. Okay, that's it. So this is your bending moment diagram. So if you want to do, see to the scale point of view, this is how exactly it look like, right? And WL and this W. So that's all about the shear force and bending moment diagram construction for cantilever beams using the concept of load shear force bending moment relationships. Thank you.